Okay, let's start our lecture. So on Monday, we talk about the definition of reliability for bulk electric system, BS. There are three basic requirements for bulk electric system to be stable. The first one, voltage, frequency, they should stay within their limits. And all the signal generators they need to be need to be synchronized. So which means they'll be running in parallel. And the third, the entire network need to be a integrated network. So there should not be islanding or separation. So those are the three fundamental requirements for electric power system. Here we talk about the BS, bulk electric system, to be reliable. To address any reliability concerns, there will be a two-stage. First is the planning stage, which is before any event happens. For the planning engineer, they need to design the reliability standards, such as if you follow the standard, and the system should be fine for maybe almost 100% likelihood, which means those standards should avoid any violation of reliability requirements. But in reality, when the system encounter any disturbances, in case the disturbance has not been studied by planning engineers, the operator will try their best to follow all the existing standard, but there may still be some issues. So which means in reality, reliability standard, even you meet the standard, system may still be insecure, but you will try your best. You should not intentionally violate any standard. Sometimes the violations are not intentional behavior, such as if the operator have enough data, based on the data, they check the standard, they know what action to take, right? Or what action not to take. But what if they don't have enough data, so they can make the wrong decision? So that can be the cases. So violation might happen in reality. To ensure the reliability, so we need to deal with a lot of scenarios, all possible scenarios. So NERC put all such scenarios into the categories in this table, starting from P0 until P7. So P0 means basically normal condition. The system doesn't lose any element. We call it a normal system. Sometimes we just use N-0 to indicate. N means the total number of elements of the regional system. 0 means it doesn't lose anything. Starting from the second one, so you will see there's N-1, which means you're going to lose a single element. But systems still need to be safe, meet all the standards, like voltage, frequency, and the signal generators, and also the integrity of the grid. And this one, P3, is called N-1 So it studies a base condition, which is already N-1. And then you lose one additional element. So this one could be one of the conditions from maybe second or third category. Before you fix this problem, and another contingency happens. So you're going to lose one more element. And there's also a category you just lose the two elements together at the same time, starting from N-0. From N-0, you lose another two elements, so that'll be N-2. Yes, this is also N-2. So there will be more detailed situations for any contingencies. Actually, you may ask, what if the system loses more than two elements? So usually they will use terminology like either N-3, or they just simply put N-K. K here can be any number bigger than 2. So that one can be considered. Some utilities definitely they need to meet all requirements in this table. Additionally, they need to do some study for MSK. But MSK can be the total number of MSK scenario can be huge, because if you think about any transmission grade, even as we said, we have 4 interconnections. So right now we're in the Eastern connection. So even we're connected to a TVA power system, but TVA power system is tightly connected with the rest of the system in the Eastern connection. So if you bring the Eastern connection model, the system has 70,000 substations for the bulk power system model. So if you open the bulk power system model, it has 70,000 buses or substations, including transmission and some sub-transmission. So MSK with MS1 means 70,000. If we talk about just your loss of a substation, but you can also lose a circuit, like a transmission line, or maybe some transformer. So if you also count transformer, transmission line, the total number is now 70,000. It could be maybe 200,000, right? There's so many elements. So even MS1, it can be huge number, right? MS2 will be this number multiplied by the number, and MS3 will be such number cube. MSK, that's very large. Even you think about as a TVA engineer, why do I need to study a contingency in New York? Maybe let's focus on the element inside of the Tennessee state or this territory. That's still huge. So the transmission grid may have element about maybe several thousands element in Tennessee state. So that can still be huge. So finally, most utility companies, they will study, if they have to study MSK, which usually means if I lose a substation and all the lines, no matter how many, it can be 3, 4, or 5, if they're connected to the same substation, all the lines will be lost. So that has to be studied. Okay, even that doesn't fall into exactly any role in this table, but that should be studied. Okay, so that's the table is too complex. I just want to give you some ideas what type of contingency should be studied, what type of contingency are not worth even study. Okay, or some contingency, even you study as much as possible, there's not much you can do. Okay, so how can we allocate the existing human power resources to work on the most important contingencies? This table is not very good to visualize what risk the system may encounter. So we can visualize all contingencies from previous table in this plot. So this plot X is the consequences, or you can just simply call it cost if you just measure this one by dollar. The Y is the likelihood, or you can just mathematically speaking, you can call it a probability, the same thing. So close to origin, that's low cost and the low probability, and moving along with each axis, you will have either high cost or high probability. Okay, so then those contingencies, some contingency we know if you only just lose a single element, that probability can be high, right? Because there's a lot of reason you can trip one unit, but losing a single component may not be a really big deal to the entire system. So such like MS1 contingency, either you lose a single generator or you lose a single line. Those are the green and the blue dots. So usually they will in the area with high likelihood or high probability but a low consequence. So they will align here. For some other contingency, like if you lose 2 elements, it could be N-1, -1, or MS2. Usually they will have a lower probability but bigger cost. Okay, so they will stay in this area. And there could be some extreme event like MSK. This could be cascading failures or hurricanes moving the entire transmission path. No matter how many lines in the path, they will be gone. So those will have very low likelihood because they don't happen every month or every day. They may happen once a year or once several years. But once any such events happen, the cost can be extremely high. So they will be called extreme event. So you can see all the contingencies stay along this hyperbolic curve. So which there are reasons, because if you multiply the cost by the probability, so you can come up with the index, you can call it the risk. So all the contingency will have about the same risk level. All right. So, but you may wonder why that the contingency all stay along with this curve but not there, because if there's another curve with this one will have much higher risk. So the planning engineer, when they design the system, upgrade the system, they need to make sure they try to push this curve as close to the X and Y axis, right? So if you have another system which is like this curve, the system is poorly designed. Or we can just say, if we partition the entire the plan into 4 regions, this region is like a high cost, high likelihood region. This should never happen. As planning engineer, you need to make sure if any contingency happen which can cause problem, they will stay close enough to the X or Y axis. But how about this corner? This corner means the cost is very low and the probability also very low. So why do we need to study it? Right? It's not worth even studying this one. Okay, we just ignore this one. So finally, we have pretty much all contingency the planning engineer need to study will be around those 2 regions. Or finally, they will stay along with this curve, with roughly about the same risk. Then you think, okay, the previous table we cover n-1, n-1, -1, n-2, but we didn't cover n-k. But they still have very high risk. Even the probability is very low, but once they happen, they will have a lot of consequences. So how should we cover those? If you want to continue, such contingency will continue forever, right? There will be always even more extreme event that can cause huge costs. That can make your entire system in blackout, lasting for several days or even months. That's what happened in some of the historical blackout. But engineers, they only have very limited time. They cannot cover everything. So the idea is we identify some of those extreme events which have a slightly higher probability. Then we only cover those. And for the rest, we just selectively pick some of them to study. Okay, so that's how we come up with this table. So if we visualize the different categories of the table on this map, on this plot, so P0 is just normal condition, right? So that should be, we don't need to worry about this one. So starting from P1, P2, that's MS1. So that's usually stay in this blue region. And P3 to P7 is actually especially about MS2. But for the extreme event, we only select some of them to cover. Which to select? One idea is there are some studies. We have, for the planning engineer, they may have base power flow condition, which means it can be operating condition representing a typical day. So they will run all the contingencies from a previous slice, all the combination. And then they can reduce the load, maybe by a certain percentage, and redo the study. And then can increase the load, also do some studies. Basically, they cover light load condition and peak load condition for the maybe long enough time frame. And there's some research that find, so if the load is light, and the risk will have a curve which come with exponential tail, which means, so this purple curve will become this green one. I draw it in red, which means for the extreme event, they will not happen at very high probability. So most of the event, if it happen, they won't cause a lot of cost. So if for light load, they can focus on maybe the blue region and the part of this orange region or yellow region. But when the system load is high, the risk curve will have a heavy tail, which means it will not be a purely ideally hyperbolic. So maybe at the end, they will just suddenly go up, which means extreme event, they may have they will increase their probability. And they will focus on which extreme events can suddenly increase the probability. Like for example, I gave you one example. If the load increase in one area, all the lines sending power to this area will have more probability to be congested. So if you add contingency on those lines, that can trigger more contingencies. So they can focus on some of the MSK scenarios, and then they just ignore the others. Okay, so that's the basic idea on how to select a contingency to study and also cover some of the MSK scenarios. Any question? All right, so next we need to introduce some terminologies. The first one is operating quantities. Okay, because we need to study the security, dynamic, and stability about the power system. A power system has many variables or parameters, and we as engineers or operators, they don't need to check every single variable parameter. They only select some of them which can fully almost enough to represent the security condition or reliability condition of the system. So usually such quantities a power, real power, reactive power, apparent power, or voltage and current. For voltage current, they measure the RMS value, the root mean square value, and the phasor or phasor value. So basically power, voltage, current of the system will be the most important one to monitor and to check the reliability of the system. Later we can add frequency if the frequency can change. The next term is the steady state operating condition. A steady state operating condition is a condition of the system in which all operating quantities that characterize the system can be considered to be constant, only for the purpose of analysis. But those quantities are not constant. So if you're able to measure the voltage, power, current, even there's no fault because the system has the load change all the time. So you will see the voltage, current will fluctuate at very little magnitude, but stay pretty close at around the same value, around the nominal value. If that's the case, we can utilize some steady state analysis method, focus on the steady state condition. Then we can treat those operating quantities as constant. Then we call such condition as the steady state operating condition. But it doesn't mean those variables will be constant. It just means their variation not important. The next term is synchronous operation. Synchronous operation means a synchronous generator or synchronous motor, or we can just call it a synchronous machine, is in synchronous operation with another machine or the network to which is connected if its average electric speed is equal to the electric speed of the other machine or system. So if you have two synchronous machines connected, one as a generator, the other as motor, one is the source, the other as load, their electric speed, average electric speed, should be equal. If that's the case, the two generators are operating in the synchronous operation. Why do we use the electric speed? Because their physical speed can be very different, depending on how many poles you have. In order to generate 60 Hertz electricity, AC electricity, if the generator only have 2 poles, such as round rotor generator, you may only have 2 poles. So the rotor speed, actual speed will be 60 times in 1 second, which is 60 Hertz. If you can have 4 poles, like 2n and 2s, then the rotational speed can be 30 hertz because you have a full pulse. So the electric speed can be 60 hertz, right? If you remember if we compare the hydro generator versus the thermal generator, the hydro generator usually have a fewer pulse. Oh, sorry, more pulse. And the thermal generator usually have a fewer pulse. So the hydro generator usually operate at much lower speed. But when they connect to the system, the electric speed are about the same. A power system is said to be in synchronous operation if all is connected. Synchronous machines are in the synchronous operations with the AC network. Okay, this is one example after a disturbance, and each curve represents synchronous generators regarding the electric speed or frequency in hertz. So the center frequency is 60 hertz, right? So it starts from 60 hertz. After some disturbance, finally, all generator will have a frequency pretty close to 60, not exactly 60. So it will slightly go down. So probably this event is just a loss of a single generator. And the frequency declined a little bit, but still very close to 60. Probably for this case, 59.99 hertz. And we'll see all the generators actually in synchronous operation. And this power system is in synchronous operation. If we let the simulation continue, eventually the variation on the frequency will be smaller and smaller, and you can see the system go back to steady state operating condition if the frequency variation can be ignored. Next one, power system stability. This is the one of the theme for this course. We are going to talk about power system modeling, control, and stability. Power system stability is stability of a power system for a given initial operating condition to regain an acceptable stable state of the operating equilibrium, either original or different, after being subjected to a disturbance. So basically, it talks about after falling any disturbance, if the system is able to reach safely to operating equilibrium, then the system is stable. The stability of a power system is concerned on the state variables that are defined. Because the entire power system has so many variables, some are variables of its generator, some with a transformer, some controllers, and there could be or even very detailed control logic in the power plant. As the power system operators, if you want to make sure the entire system to be stable, some very detailed variables are not very important. So they want to focus on only the operating quantities, which are such as the voltage, or current, or power, or frequency for the most important variables. So they will define the state variables. So they want to make sure those state variables are able to go back to the equilibrium after a disturbance. If we consider interconnected multi-machine power system as a whole, so the stability problem is mainly just to maintain the synchronous operation of all synchronous generators. So which means all synchronous generators can maintain their synchronous operation, the system is stable, which include the generators and motors. For motor, we talk about the synchronous motors. Sometimes if you study a part of the system, because system can be huge, but if you study only a single power plant, small generators, you may notice a particular generator or group of generator may become unstable, which means they will lose their synchronism with the rest of system. But if that generator is not important to you, you can simply trip that generator, and your main system will keep the stability. So the question will be to either the operator to this local power plant or to the operator of the entire power grid. So if you ask the operator at this power plant, definitely that's unstable because his job is to maintain the stability of this power plant, and you have to trip this generator to avoid any damage. So that definitely is become unstable. But if you ask about the operator for the entire power grid, because if this power plant is very small, it doesn't impact the system. So this instability may be ignored by the grid operator. And for some other cases like motors, motor with load, they can lose their stability. One example is some motor, they can stall, which means they can be tripped or protected by the local controllers. But that doesn't cause a lot of change on the entire the BES, the bulk electric system. Then such instability can be ignored. Okay, so I want to just give you the idea starting from the more mathematical definition and then more engineering definition. From mathematical point of view, a power system is a nonlinear system. Okay, it has many state variables. And if all state variables, they can go back to their equilibrium, the system has to be stable. But in reality, when you operate a very large interconnected power network with a lot of power generators, and if you ask the stability question to the operator, they only monitor the most important ones. Okay, so they can reasonably ignore some of the small generators, even if they become out of step or lost. They lose their synchronism with the system, they just simply trip the generator. So such instability can be ignored. So starting from this slides, we'll focus on the major system, the BES or BPS. We ignore some small generator stability problem. Next, we want to talk about what a disturbance is. It is a sudden change or sequence of change in one or more parameters or operating quantities of the system. There are two types of disturbances. The one we just call it a small disturbance. A small disturbance compared to large disturbance, usually small disturbance means what exactly happened during this disturbance is not important at all to the engineer or to the operator to monitor the system. What can this disturbance be? For instance, if the load changed just slightly, you don't have to identify which load, exactly load is changing or has been changed. You just study whatever the system dynamic after the change. So the location type of the disturbance is not very important. Another example is if I'm an operator of the TVA system, a line trip happened in New York State because that's far away from me. So I may be able to detect that change. If there's a line trip in New York State, which will cause some a little bit oscillation, I can detect that, but I really don't care what that is. It's equivalent to maybe load fluctuation in my area. So if the contingency can be that small, the system model can be linearized. We can use a linear system model to study the response of the system, because linear system always assume the motion of the system can be can be proportionally changed with the size of disturbance. So it doesn't matter to study either large or small, they will give you the same conclusion. But compared to small disturbance, a large disturbance means we have to know what exactly happened with this disturbance, whether it's a line trip or generator trip location, because we need to simulate this disturbance in our system model. And if the system model is nonlinear, we cannot linearize, because all the details of disturbance may determine the final response of the system. Examples such as a short circuit fault, a loss of a generator or load. But go back to my examples. If I'm operating the TV system, even a line trip or generator trip in far away from my system can still be treated as small disturbance. The key is what exactly happened doesn't change the result of your analysis. If this one can be met, so that contingency will be small. If this one is not true, then you have to treat this contingency as large disturbance. Give you very simple examples. If we use these two equations to model how the a single generator respond to any disturbance. Those two equations together are called a swing equation. We'll learn this one in next session. The first equation tells how the speed will change if the input mechanical power and output electric power are not equal. So if the input power is bigger, then the speed will increase, right? Will become positive. Then the angle will increase. So for this function, the electric power, if it's just single generator connected to a large system, this function is very simple. It's just sine function. It can be calculated by the active power flow. If you still remember the active power transfer through a single transmission line from 421. Do you remember what that formula is? So that single transmission line, the first terminal has voltage V1, the second V2, right? Divided by X. X is the total reactance. Then this function will be sine delta. Everybody remember this formula? Okay. So this is a nonlinear function, a sine function. So if you visualize this function, this only visualize part of this sine function. Delta 0 is a current operating condition, and P0 is the current, the electric power, right? So then this point will be the current operating points. So even this curve is nonlinear, but near this operating point, if we look at very small disturbance, which can only move the system away from this point at a very small distance in very small neighborhood, we can linearize this curve. Like for instance, if the disturbance will not move the system outside of this blue region, and if we draw the tangent line at that point, so the blue line and this magenta or pink curve, they're very close. The difference is not important at all. If that's the case, we'll instead of using this pink curve, we'll just use this linear curve. Then we use this linear curve in this equation, so the equation becomes linear equation. So you can use your linear system method to study it. It's very much similar than the linear system. But if you have disturbance, can push the system outside of this region to this bigger rectangular area. So you see the two curves are very different, right? So the difference will affect the result. So you have to go back to the nonlinear curve. So stay inside of this blue region, the disturbance can be considered small, but outside of this region, when the linear approximation is different from the regional nonlinear curve, so you have to treat this disturbance as a large disturbance. So there's not a phase standard saying which contingency this list will be always small, that list will be always large. The questions will be asked to the engineers, operators, so what accuracy they want to achieve. Okay, so if you ignore the details of the disturbance, it doesn't affect accuracy of the analysis, so disturbance will be small. If you have to consider very detailed, like location, the size, or the circuit involved in the disturbance, that has to be large. So you need to utilize the large disturbance analysis. Any question? So why do we need a dynamic analysis? So when we design and operate interconnected power system, right, its dynamic performance subject to a change, either small or large, need to be considered. So it is very important when all the change are finished, ended, so the system can settle down to a new operating condition without violation of constraints. So this sentence had two requirements. The first one, when the system, after system reached a new operating condition, the new operating condition has to be reliable. They need to meet all the reliability standard. The second requirement is the process transitioning from the original condition to the new condition should not violate any standard. Not just the final location to be reliable, the entire path has no violation. Not only should the new condition be acceptable, which means it reached another steady state condition, the system must survive the transition to the new condition. So that's why we need dynamic analysis. Like if we use this case as one example, right? We know what disturbance at. Like for example, we trip a generator. We can always use power flow to resolve power flow. We solve the power flow before the contingency and after contingency. After power contingency, if we solve power flow, the power flow can still be solved. That gave you a steady state condition. So that gave you condition here, but you still need to do the dynamic simulation to make sure there's no generator is flying away, right? If that happened, so that system cannot survive this new condition. So we need to do the simulation to find the dynamic of the system. Then we can give the conclusion the system is reliable after this contingency. A practical example is this one. This is a criteria with NERC, especially talking about voltage performance after a single contingency. This is related to one phenomena which is called fault-induced delayed voltage recovery problem. So this problem is because a power system may have a lot of motor load in the summertime. If the voltage become low, some motor will stall. So the motor will change from like a resistive load to a more inductive load. So that will lower the voltage. So in California, in Southern California, in the summer time, if even just a single contingency, it doesn't cause the instability of the system, but that they will delay the voltage recovery. So there was one event, one substation recover voltage after 30 seconds or even longer time. So then they designed this criteria for the planning engineer to study contingency to make sure the voltage can be safely recovered back to the nominal value. So you can see there's a plot. This curve just indicates a typical curve after any single contingency. So this the Y is the voltage magnitude, S is time. So after the fault is clear, this is the lowest voltage magnitude. After fault is clear, the standard says the post-fault voltage dip, which is the lowest voltage after the fault is clear, should not exceed 25%, which means this voltage should be 0.75 per unit based on the base value. Okay, so if this substation is 200 kV, 230 kV, so that will be the lowest voltage will be 75% of the 230 kV. It cannot be lower than that one. If it's lower than this one, so the power company need to figure out what contraction they can do, or what maybe they can add capacitor to support the voltage or some other controller. That's for load bus. If the bus has no load, it's just a substation having connecting other transmissions, so the voltage can be 0.7 per unit. The second sentence says the voltage dip should not exceed 20% for more than 20 cycles. Okay, so if the first one can be satisfied, but which means they can, here is higher than 0.75. And when it go back, but there will be some oscillation. But you can see this waveform will temporarily go down. And if this line is 0.8, this is the duration for the voltage temporarily become lower than 0.8. That duration should be less than 20 cycles. 20 cycles is 0.33 second. If it's shorter than this one, that is safe. That's okay. All right. So that's not finished yet. So if this is satisfied, and the last sentence said after some time, at that time usually will be 1 minute, maybe after tenths of second or maybe 1 minute. So the voltage need to go back to this very narrow envelope. This envelope is 5% from the nominal value. So they need to go back to 0.95 and stay above 0.95. So if this is satisfied, the entire transition is safe. So in order to check this criterion, so the engineer have to simulate each individual single contingencies, especially for those close to motor loads. So this is one example. Even the system never loses stability, but we still need to do a dynamic study to know the actual response. We will come back to this criterion in the voltage control section, voltage modeling and regulation section. We will talk about how we can mitigate this problem. All right, so before the end of this section, the end of this lecture, I want to talk about 3 terms, very related terms. The 3 terms, the first one is insecure, the second is unstable, the third one is oscillatory. Maybe you also add the counterpart, the insecure versus secure, unstable versus stable, oscillatory versus non-oscillatory. So you can, when you talk to power system engineers, you often hear some engineer just say, okay, so during this event, and our system become insecure, and some generator unstable, some other stable, and one generator is oscillatory, or maybe oscillating. So you will see all the 3 terms, they just use together. But what are their differences? That's what we need to make it clear in this class. What does insecure mean? So insecure really means violating security criteria. Okay, because you have a criteria standard defining what security means, then violating such criteria will be insecure. Not violating those criteria will be secure. There could be cases the criteria are not well designed, it's poorly designed. Which means if you meet all the criteria, some equipment will be damaged, but your system is still considered secure because they meet all the standard. So secure, insecure here is about the regulatory issues based on who designed the standard, whether you meet the standard, basically just whether you follow the law, not following the law. The law may not be perfect, maybe imperfect, but it's just yes or no, whether you follow this law or not. That's secure versus insecure. The next one, unstable. Unstable means the system is unable to go back to go to a one equilibrium following a disturbance. If it can reach an equilibrium, the system is stable. If it cannot reach any equilibrium, it will just transitioning forever. It never reach any equilibrium, the system is unstable. So this concept is more from a mathematical or dynamic system point of view. Oscillatory means if any operating quantity changes periodically. So you can see the quantity go up and down. If you measure the voltage will vary, go up and down around some value. You can see the system is oscillatory. If all operating quantity they change monotonically, they will stay flat, or the oscillation can be ignored. You can see the system is not oscillatory. So it's mainly from the measurement of observation point of view. Okay, so what are their differences? Give you some example. If a power system is unstable, the system has to be insecure if the criteria are well designed. Okay, so no planning engineer will just treat unstable system as secure, right? It doesn't make any sense. So which means secure for well-designed standard, the secure system is like more higher requirements compared to stable system. A stable system might be insecure if the equilibrium point is, if it can reach equilibrium point, but transition will violate some standard. Right? One example would be this one. So if the system violates those standards but still go back to the steady state, it's stable, but it's insecure because it doesn't meet this standard. When oscillatory motion becomes uncontrollable and damaging to generator and other equipment, the system becomes insecure and may even become unstable. So which means oscillatory phenomenon is not the end of the world. It doesn't, if the oscillatory behavior can be mitigated, it doesn't cause any instability or violation of standard, it may be fine. Operator don't like oscillation, but it may not be really bad. It at least indicate the generator is recovering back to the or to a new equilibrium. So if you want to visualize the three the concept, the stable stay in this bubble, right? There's everything inside of this is always considered stable. If you want to draw another bubble about secure, it has to be inside of stable bubble for well-designed system and criteria. And if you want to draw another one talking about oscillatory, which may be like this one, with some, so if some oscillating system can be stable, some oscillating system can be unstable. It can be secure, can be insecure. Okay. So knowing those terminologies, so when you talk to some other engineers or in the future, you can try to make sure your statement to be accurate, right? You always hear some engineers say, okay, my generator is oscillating, so that is unstable. So sometimes that may not be true. You have to ask more details, whether finally the generator go to the new equilibrium, is there any violation of your standard? Then you can use more accurate statement about that phenomenon. All right, so this is the last slide. Yeah, we'll continue on Friday.